Explanation. So we're given, so far we're given the percentage of aluminum and sulfur, and then we're just told that the rest is oxygen. So we find that the percentage of oxygen by taking the sum of aluminum and sulfur, so 15.77 plus 28.11, and then we take 100 and subtract that, and we get about 56.12%. So that's what I got for my percentage of oxygen. So when you're doing empirical formula calculations, you just assume you have 100 grams. So in that way, the conversion from percentage to grams is really easy. So I said that I have 15.77 grams of aluminum, 28.11 grams of sulfur, and 56.12 grams of oxygen. So then what I did is I found the molecular weight of each individual element and I divided them. And the reason I divided them is because I wanted to get rid of this little pesky grams over here, so that way they both cancel out and I'm left with moles. So now I have the moles. So I have 0.5845 moles of aluminum, 0.8768 moles of sulfur, and 3.5075 moles of oxygen. So then my next step is to divide everything by the smallest amount of moles, which in this case is aluminum. So I'm going to divide by this number. Okay. So then the value I should get here is 1. I'm not getting 1 over here. Let me do that calculation real quick. 0.8768 over 0.5845. So I get about 1.50. And then for get about 6 oxygen. Oops, sorry about that. 6.0008. So obviously this oxygen is pretty close to 0. It's pretty close to 6, so we leave it. However, our sulfur is at about 1.5 moles, or for the molecular coefficient or the subscript, so to speak. So what we do is we multiply it by a common integer until we get the proper amount of, until we get integer-sized numbers for every single element. So I'm going to multiply everything by 2. And if that doesn't work, I'll multiply by 3, and so on and so forth. So, should get 3. Yeah, so if I multiply everything by 2, I should have Al2 S3O12. And that is my empirical formula. Okay, so we have magnesium chloride. First of all, this problem is a little bit different because, you know, we have to find our equation based off of the nomenclature, which is something that's common. So if we find magnesium chloride, something that helps with the charges is if you have your periodic table, the 1A, the 2A means +1, +2 charge. The 7A is -1, the 6A is -2, and the 3A is -3. So that's, you know, if you write that on your periodic table, it will make things a whole lot easier. So we have magnesium chloride. Okay, we have magnesium chloride. So we know we have an Mg and we have a Cl. And we know that magnesium has a +2 charge and chloride has a -1 charge. So then we just do our cross multiplication strategy and we get MgCl2. Then we also know we have silver nitrate. So we have AgNO3. So we know that silver, since it's a transition metal, it can have pretty much any charge. It's just kind of wonk. Like silver can have a +1, +2, +3 charge. Since I said it's just I didn't have any Roman numerals for this one. Just assume it's a +1 charge. So we have a +1 for silver and a -1 for NO3. So then we just have AgNO3. And then this produces magnesium nitrate, which is MgNO3 2. Because Mg's the charge doesn't change necessarily. If it's not a transition metal, the charges doesn't. If the metal is non-transitional, the charge doesn't change. So, and then silver chloride, the charge also didn't change. So we have AgCl. So let's just check and see if this equation is balanced. I see I have 2 chlorides here. I have 1 magnesium, I have 1 NO3, I have 1 Ag, 1 Ag. So the only thing I need to do is I need to add a 2 in front of AgCl. And since I have 2 NO3s, let me just put a 2 in front of AgNO3. So this is our molecular equation. Molecular EQ. We got that part done, so we can cross that off our list. All right, we got our molecular equation. Now we're looking for the total equation. And for this part, it's real handy to have your solubility rules. I have mine out right here. So you're basically just looking at each compound and seeing if they are soluble. So MgCl, let's see. It is a chloride. Chlorides are always soluble, except with Cu and all these other things. Mg is not on the list, so this is soluble. So we have Mg minus, or +2, Cl minus. Silver nitrate. Nitrates are always soluble, except with no exceptions, actually. So we have 2 Ag minus +2 NO3 minus. And then this goes to, I'm going to continue the equation down here. Let me separate these with a little line. That way y'all are not confused. Okay. So then we have MgNO3. Nitrates are always soluble, no exceptions. So we have Mg +2 NO3 minus. Chlorides are always soluble, except with silver, copper, silver plus, so just +1 charge. That is in fact the case for this one. So AgCl stays together, and they are neutral. They're a solid. So that's our precipitate. So that is our total equation. Total EQ. Now, if we want to find our net equation, we have to find our spectator ions. We have to cancel spectator ions. And I'm just going to highlight this in pink, what our spectator ions are. So in this case, since Mg was soluble on either sides of the total equation, that one is soluble. So I'm going to put a pink X through there and a pink X through the product side. NO3 was soluble on both sides, so I'm going to put a pink X through it on both sides. And then 2Cl and 2Ag stayed soluble, so I am going to keep those the same. Oh, sorry, this is supposed to be at 2. Sorry about that. Okay. So our net equation, our net EQ is 2Cl minus plus 2Ag plus goes to 2AgCl, and that is a solid. So that is our net equation. And for conductivity, if we want to look at our the conductivity levels of our equation, all we have to do is figure out how many free ions that we have. So I'm going to rewrite the total equation. So I have Mg plus 2Cl plus 2Ag plus 2NO3 goes to Mg plus 2 minus plus minus, okay, plus 2NO3 minus plus 2AgCl. So all we have to do is find out how many free ions that we have. And we do this by looking at our total equation. So we see that we have, since everything was soluble on the reactant side, we have 1 plus 4 plus 2. So we have 6 plus 1, so we have 7 free ions. We have 7 on the reactant side. And then we have 3 free ions on the product side. So conductivity decreases. Just to quickly go over, we have our volume, which is 53.02 milliliters. V1 is equivalent to 0.05302 liters, 0.4 molarity for M2, 100 milliliters for V2, which I equated to 0.1 liters, and then we're looking for M1 is our goal. So I have the equation M1 V1 equals M2 V2. So then I'm saying that M1, since we're looking for it, I just leave it as M1. I plug in V1, I plug in M2, which is 0.4 molarity, and then I plug in V2, which is 0.1 liters. So then, if I want to find M1, I just have to divide both sides by 0.05302 liters. So M1 should be zero 0.75443, approximately, rounding-ish. But since we have 2 H's for every HSO4, we have H2SO4, we have to multiply this by 2. Right? Yes, you have to multiply this by 2 because we're looking for the potassium hydroxide. Yes, we're looking for potassium hydroxide molarity, and we have to multiply this by 2 since every one H in potassium hydroxide cancels out one H in SO4. So we multiply this by 2. So our real molarity, M1, is about 1.50886. And if we were to